Okay, so we're now moving on to what we know as connected particles. So I've got a car and a trailer that it's pulling. So I start with my horizontal road, and two objects, slightly smaller object, going to be my trailer, and a slightly bigger object, which is going to be my car. So the car has got a mass of 780 kilograms, and the trailer's got an object of 560 kilograms. And it says here that it's been pulled by a light inextensible cable. So the cable is not stretching or compressing. We've got two different objects. So what I'm going to do, and I think is really important, is to split down the middle and look at the forces acting on each object separately. So what forces are acting on the car? So it says that the engine produces the driving force, and that is the engine of the car. So that is taking the car, let's say, to the right, 1800 newtons. Total resistant force on the car and trailer are 800 and 600 respectively. So 800 working against the car, stuff like friction, air resistance, things like that, and the trailer slightly smaller, 600. And those forces act directly on those objects. There's also forces passed on through this cable, so it's kind of halting the car, it's kind of pulling it back, and it's the thing that is directly pulling along the trailer. Okay, so this 1800 newtons is not acting directly on this trailer. It's the bar, it's the cable, it's this tension in the cable that is kind of acting for that. There's one more thing that so that's my positive direction. Okay, and then what I'm going to say is that we're going to look at three different things. Okay, in fact, before we start looking at A, B, C, these three different things. So it's forces acting on, so it's the F equals ma, the forces acting going to the right on three different things. Firstly, the car, secondly, the trailer, and thirdly, the whole system. And I think it's important to just kind of, especially when you start doing these, consider all three different possibilities. And then maybe when you do questions, you'll know kind of which one you want to pick out without doing all three. So acting on the car, we have got 1800 newtons, take away 800, and then take away this t which is acting against as well, and that is equal to its mass 780 times by acceleration unknown. If we look at the trailer, we've got positive, so we've got t minus 600, that's it, equals 560a. And then the whole system, which can be gained by combining these two equations or just looking back at the diagram, which is 1800, take away 800, take away 600, take away t plus t equals the combined 780 plus 560a. I'd normally probably just add those straight together. But since we need to simplify what's going on here anyway with the t's, I thought I'd just show it like that. So this will simplify to 1800 minus 800 minus 600. Obviously that simplifies as well, but just in terms of seeing the forces, equals the t's will cancel out, and then we'll end up with 1340a. So I've got three different possibilities here, and now it's about what do we actually need for the question we're doing. But I think it's a really important thing to do to kind of sit down and look at the different possibilities you can come up with. And it's something, if you look at the Madders Maths connected particles, they do really well, I think. As well as splitting this diagram in half effectively to allow us to do this. So first of all, to find the acceleration, it looks like this bottom one here has got the least number of unknowns. So I'm going to take equation 3 that we've written down, and the left hand side is going to simplify down to 400, so we'll get 400 equals 1340a. But again, having done that, I want to have seen these first, which I have written down there. And then a is going to equal to whatever 400 divided by 1340, which to 3 sig fig is going to be 0.299 meters per second squared. That's the final answer. When I use that in a minute, I'm going to probably use the version of my calculator that's slightly more accurate. So part B, find the tension. So we need one of these two equations that have both got tension in them. And hopefully what you can tell is that equation number 2 for the trailer is easier because it's got a positive t on it. So we can now just say t minus 600 equals to 560 times by 0.298. And again, I'm just literally going to use the button in my calculator that saves that number. So it's going to be answer times by 560 and then add on 600. To 3 significant figures, it gives me 767 newtons. Okay, that's fairly straightforward. It's all about the quality of your diagrams and your understanding about splitting it into different forces on one object at a time, as well as the whole system. And as I said, you could just add these two together in order to create that bottom one directly. Or fire this one even first. Right, so some particle model assumptions now. So how have we used the assumption that the string cable is light? So that means that we ignore the mass of the object. And if we ignore the mass of an object, we can't do any F equals ma on it on the cable itself. So we kind of just have it as an intermediary item rather than doing F equals ma and looking at the forces on the string / cable as well. And how we use it in an example, we said that the tension is the same throughout, and the same is true of the acceleration. The tension and acceleration, which wouldn't necessarily be the same if it did kind of stretch and stuff. You'd maybe have an inconsistency there in your tensions and accelerations throughout the system. Okay, but this A, this A, and this A, all the same value because of that. And then again, this T and this T, by definition, those two both the same as each other.